Hello class, welcome to our Calculus 2 lecture for Wednesday, April 22nd. This is going to be our last lecture for the semester, although Monday, April 27th is actually the last official class day. We will not have a new lecture on that day. We're going to finish the material today so you can prepare for the test number 3, right, which is coming up on Monday, April 27th. Here is the announcement. So I've already talked about this in previous lectures, but here's the announcement for the test, right? The sample test is posted now, and there are the instructions for how you're going to take the test, but it's very similar to how we did test number 2. So I will post that test at 1 p.m. on April 27th, Monday, April 27th, and you can return that to me by email, right, in PDF format by April the 29th, which is Wednesday, right, by 1 p.m. And then I will grade those and email those back to you just like last time. So the sample test is posted, as I mentioned, and so on the day you're watching this, which is Wednesday, April 27th, then I think that is going to be Taylor's test review, right, at 1 p.m. So I hope you had a chance to attend that test review. I will post the answers to the sample test by this weekend. So you will have those to look at to help you correct your mistakes on the sample test prior to the test. I also have to post the answers to test number 2, although that's a little bit less urgent, right? But I do want to post the answers for test number 2 as well, so I need to post those, and I need to send you instructions for how the calculus flux is going to work, right? Okay, this semester. It's going to be similar to how I described it in the syllabus, but we might make a few adjustments based on, of course, the circumstances have changed, right? So I will send those instructions to you on how to use your calculus flux hopefully by the end of this week. So I've still been entering your flux dollars for attending Taylor's SI sessions. So those are up to date through last week. And of course, we will still get flux dollars for the attendance policy. And I mentioned how that will work. It's going to be based on your attendance prior to spring break, right? When we were taking attendance physically, of course, and then your participation after spring break, right? Have you been keeping up with the homeworks, right? And of course, well, everyone submitted the test. So I think, if you've been taking, if you took the test, right, that will also count. Test number 2 and test number 3, that will also count for your class participation. So I think most people can get the 25 flux dollars for the class attendance policy. There might be a few exceptions to that, but I think most people will qualify for those 25 flux dollars plus flux dollars for your homework average, right? If you've been keeping that up, and then flux dollars, depending on your midterm test scores. So I've already, of course, updated your flux dollars for your test number 2 score, and then I'll update it also for your test number 3 score. Okay. All right, so that's pretty much sort of where we are in terms of homework and taking tests and so forth. So that's where we are in terms of the class schedule. Your test now, remember, will only cover through this homework, 9.2, 9.3, which we talked about on Monday. So we're through talking about this. I am going to talk about some new material today, but this will not be covered on test number 3. This homework about comparisons of series, these are 2 advanced techniques you can use to determine if series converge or diverge. So those will not be on test number 3. So there are no problems from this homework on the sample test number 3, and there won't be any on test number 3. This homework is not due until Friday, May the 8th, so it's a long ways off, because that is also the day that the final exam will be due, okay, to be turned into me if you have to take the final exam. the final exam will be posted May the 6th, which is Wednesday, and then it will be due on May the 8th. So that's when this homework is also due. And problems from this homework may be on the final exam, but this homework will count into your homework average. Okay, but you've got plenty of time to complete that prior to the end of the semester. It's not a lengthy homework anyway. Some of the problems might be challenging, but it's not a super lengthy homework. Okay, so I hope everyone understands, how things are going to proceed from now on. So, because I'm not going to be really talking to you directly again unless you visit me during my Zoom office hours, right? I won't be talking to you directly again for the rest of the semester. Okay, since I won't, since this is the last lecture video that I'm going to be taping. We have done pretty good on getting through the material for the course. We missed a little bit, just a couple of sections here at the end of chapter 9. So that was unavoidable given the situation, right? That we were going to fall a little bit short on the material, but we did pretty good. So so I feel pretty good about where we got in the course, and you should feel good about your accomplishments in the course as well, right? If you've been keeping up with your homework and doing your tests, that's really a significant achievement given the situation that we found ourselves in this semester. So I applaud you for that and congratulate you for your work. I hope everyone is doing well. I'm doing fine, so I hope everyone is safe and sound, okay, and ready here to finish the semester. I know you're busy with your other classes as well in addition to this class, so you're probably really feeling overwhelmed, but it will be over soon, okay? So just hang in there, do your work, and in a few days the semester will be done, and then you can relax a little bit, and maybe the lockdown will be lifted also soon, right? So you can get out of your house or your apartment a little bit more frequently if you've been, stuck at home like I have been, right? So I'm looking forward to that as well. Okay, so I think I said everything I wanted to say. May have forgotten a few things, but be reading the announcements, right? Because if I forgot something, I'll try to make sure that I mention those in the announcements that I'm posting on Blackboard and emailing to you. All right, so let's dive into the notes here today and finish this last set of notes, right? And so you'll be ready to do that last homework when it's due, okay? And so today we're going to talk about more advanced techniques for determining whether an infinite series converges or diverges. And there are actually two techniques, but they're related to one another. The second version is kind of a simplification or a shortcut of the first version. So these are called the direct comparison test and the limit comparison test. So again, these are tests to determine if a series converges or diverges. So we have seen, I think 2 or 3 situations where we can determine if a series converges or diverges, right? Let's see, we have the term limit test, right? And then we have the integral test. And then we also know if we're dealing with a geometric series, we know if it converges or not, correct, right? And if we're dealing with a p-series, so remember from the notes last time, if you can recall what a p-series means, we know if the situations in which p-series converge and diverge, right? So we do have information already about whether a series converges or diverges, but we're going to learn just a couple of more techniques that we can use to make that determination. Remember, that's really sort of the fundamental question when you're looking at an infinite series, right? Does the series converge to a finite sum, or does the series diverge? Does the sum of the series diverge to infinity? And a secondary question is, if the series does converge, what does it converge to, right? So if a series does converge to a finite value, so if the terms of the series add up to a finite value, what is that finite value? But that's a much harder question to answer. And these two tests are not going to help us with that question, but they will help us with determining if a series converges or diverges. All right, so let's jump into the first test here, okay? And so this is called the direct comparison test. And so how this test works is if you are given a series and you're trying to, again, determine if it converges or diverges, but if the terms of that series look like the terms of a series that you already know converges or diverges, then often by just comparing the terms in those two series, you can determine if the new series converges or diverges, right? So that's why this is called the direct comparison test, right? We're given a new series, we're trying to decide, does it converge or does it diverge? But we notice, ooh, this series looks like another series that we already know about whether it converges or diverges, right? Okay, and so we can use sort of the comparison between those two series, right, to get information about the new series, right? So we can use our old knowledge of the old series, right, to help us determine what happens with the new series. That's just what is embodied here in this direct comparison test, right? So what the direct comparison test says is, look, if you've got two series, so these are the B sub n and A sub n are the sums of the series, are the terms of the series, right? Okay, and suppose you know that for the one of the series, okay, the terms are always less than or equal to the terms of the other series. So suppose you go term by term, and you can tell that for one of the series, the terms are less than or equal to the terms of the other series. Okay, so one of these series kind of dominates the others, right? The terms of one of the series are bigger than or equal to the terms of the other series. Then if you have knowledge about one or two of if you have knowledge of one of the series, that can give you information about the other series. For example, if the bigger series converges, so if it already converges to a finite sum, you know that, right? Okay, then the smaller series must also converge, right? See, that kind of makes sense, right? So again, you've got these two series, right? And maybe the numbers, the terms in one series are always bigger than or equal to the terms in the second series, right? Then if the bigger series already converges to a finite number, then that means the smaller series has got to converge too, right? Because it's going to add up to a smaller value, correct, right? On the other hand, if the smaller series, if you already know that it diverges, so if you already know that the smaller series doesn't add up to a finite value, then that means the larger series is not going to add up to a finite value either, right? If these terms are bigger than these terms, and these terms already sum up to infinity, then the larger series is can't converge either, right? There's no way it can add up to a finite number if the smaller series already adds up to infinity, right? So you get the idea here. You're looking at two series, and you know for some reason the terms of one of the series is always bigger than or equal to the terms in the other series. Then if you have knowledge about the convergence or divergence of one of those two series, that can give you information about the other series, right? I want to point out here that in this statement of this theorem, this says that the terms of one of the series is always bigger than or equal to the terms of the other series. Notice this says for all of your indices, right? One of the terms of the series is bigger than or equal to the terms of the other series. But it doesn't really have to be for all n, okay? Doesn't have to be for all n starting at 1. If one of the series dominates the other, so if the terms of one of the series dominate the terms of the second series, just for beyond a certain index, but doesn't have to be all indices, but if that happens beyond a certain index, then this theorem will still apply, okay? So you can still draw the same conclusions that you can here. All right, so actually this theorem is stated a little bit stronger than it needs to be. All right, okay, so look, all right, so that's all just a very abstract explanation, but let me show you how this works in practice, because it's a little bit easier to understand when you see it in practice. So here's our first example. What we're looking at is this series, and we're trying to decide, does that series converge or does it diverge? So the terms of the series are 2 plus 3 to the nth power, right? So if you write out, some of the terms of this series, right, you would get, let's see, when n is equal to 1, you get 1/5, right? Because you would have 2 plus 3 to the first power. That would be 2 plus 3, so that's 1/5. And then the second term is 2 plus 3 squared, so that looks like that's going to be 11, right? 2 plus 9 is 11. And the third term is 2 plus 3 cubed. Well, 3 cubed is 27, so 27 plus 2 is 29, right? Okay, so the third term is 129. So here's what this series looks like: 1/5 plus 1/11 plus 1/29, etc., right? Okay, and we're trying to decide, does that series diverge or does that series converge? All right. Okay, so what we're going to do now is, again, compare this series to a series that we already understand its convergence or divergence. All right, and the hard part here is picking out, well, what series am I going to compare this to, right? Okay, so 1/2 plus 3 to the n. What series does that kind of look like? Well, look, notice if you kind of ignore the 2 here, right? If you kind of just cross out the 2, then notice the series that you get is 1/3 to the nth power if you just ignore the 2, right? And so this series and this series, see, they sort of look alike, right? Okay, they're just slightly different from one another. So I'm going to compare 1/2 plus 3 to the nth power plus to just 1/3 to the nth power without the 2. All right. Now, why is that helpful? Because I know something about this series. Look, 1/3 to the nth power, you can rewrite that as 1/3 to the nth power, right? Okay, 1/3 to the nth power is the same as 1/3 raised to the nth power. But this series is a geometric series, right? That's a geometric series. The coefficient here is 1, so the a value is 1, and the r value, right, the so-called ratio of the geometric series is 1/3. But 1/3 is less than 1, and you know that in a geometric series, right, when you have a ratio of less than 1, right, that means that the geometric series converges. Actually, you can even calculate what it converges to, right? Isn't it, what's the formula there, right? Isn't it a over 1 minus r? Something like that, right? Okay. Actually, I think that that formula only works when the index starts at 0, and here we're starting the index at 1, so let's ignore that formula. But that's not important what the series actually converges to. What's important here is because the ratio is less than 1, we know that the series converges. So what we're hoping to do is to use our knowledge of this series, the sum from n equal 1 to infinity of 1/3 to the nth power. We're going to use our knowledge of this series and the fact that we know that it converges, right, to help us understand if this series converges. All right, so so how can I apply that knowledge of this series? Well, what I need to know is it true then that 1/2 plus 3 to the nth power, is that always going to be less than or greater than 1/3 to the nth power, right? If I can figure out the relationship, right, between the terms of this series and the terms of this series, then my knowledge of this geometric series can help me understand what happens in this series. Well, look, what is the relationship between 1/2 plus 3 to the nth power and 1/3 to the nth power? Well, of course, these quantities are very similar, right? Okay, but this is going to be this side is going to be a little bit smaller, right? Because notice in the denominator you're adding the number 2, and when you increase the denominator of a fraction, you're going to make the fraction smaller, right? So since this denominator is a little bit bigger than this denominator, that means that 1/2 plus 3 to the nth power is less than or equal to, actually less than, I think, right, 1/3 to the nth power, right? but that is enough, okay? So notice every term of this series, right, is going to be less than or equal to the corresponding term in this series, right, because this inequality is true. So since this series converges, this adds up to a finite sum, right? Okay, that means this series must also converge, right? Because this is going to be a smaller sum, right? Okay, because the terms of this series are smaller. So if this series adds up to a finite number, this series must also add up to a finite number. I have no idea what it adds up to, okay, but I know that it converges. And then this is because of its comparison with this second series that I know already converges. That's the direct comparison test, right? Okay. See, we can tell this sum is going to be smaller than this sum because these terms are smaller than these terms. I know this sum is finite, so this sum must be finite as well. That's just that simple logic. That's pretty easy, right? Logically, it is pretty easy. The problem comes in using the direct comparison test in figuring out what series, if you're given a new series, what series you want to compare it to. That's always the tricky part, all right? And that requires a little bit of practice to, sort of learn how to do that. Let's try a second example. All right, so here we have this series, 1 over 2 plus the square root of n, okay? And I want to know, same thing, right? Does that converge? When I add up all these values, does that converge to a finite number, or does that diverge to infinity? Does that sum add up to infinity, or does that sum add up to some number less than infinity, right? Okay. All right, so we're going to try using, the direct comparison test, which means I have to have something to compare this series to, right? So I need a series that I already know about, right, to compare this series to. And here's the one that I'm going to use, all right? So this one looks a little bit different, but actually these two are kind of the same. Let me show you why. I'm going to rewrite the terms of this series. Instead of using that square root, let's write n to the 1/2 power, because square root of n is the same as n to the 1/2 power, right? Okay. So notice now how these series are kind of similar. Here you have just 1 over n to the first power, right? 1 over n to the first power. And here you have something, you have a fraction that's kind of similar. You have, instead of 1 over n to the first power, you have 1 over n to the 1/2 power, but you still have 1 over a power of n, right? Okay. You still have 1 over a power of n. Just like here we have 1 over a power of n. Now, you have the 2 added in over here, right? Okay, you have the 2 added in over here, so that does complicate matters. But this is just a constant, right? The 2 is just a constant number. And as n gets really large, right, because n's going all the way to infinity, correct? So if as n gets really large, n to the 1/2 is also going to be getting really large. And when n to the 1/2 gets really large, that 2 is going to be kind of insignificant, right? So we can sort of ignore the 2 here, kind of, right? We can sort of ignore that, kind of. And if you kind of ignore that, then what you have is 1 over a power of n, and that's the same as this series, 1 over a power of n. Now, what do I know about this series, 1 over n to the first power? That is a p-series, right? Remember, when you have 1 over your index raised to a power, not a geometric series, it's called a p-series, right? When you have 1 over your index raised to a power, the index is the n value, right? Raised to a power, and the power is staying the same, but the index is changing. That's called a p-series. That's not a geometric series, right? Remember, we talked about this at length last time. In a geometric series, it's the power that's changing, but the base is staying the same. In a p-series, the base is changing, but the power is staying the same. And we know something about these so-called p-series, right? We know that they converge or diverge based on whatever this power is. Well, in this case, this power is 1. I should have written this instead of writing less than or equal to 1, I should have written 1 is bigger than or equal to 1, right? Okay, and whenever in a p-series, whenever your power is bigger than or equal to 1, that means the p-series diverges, right? If the power is less than 1, that's the good situation, right? When the power is less than 1, then the series will converge, right? Okay, but here, no, I'm sorry. Um, Sorry, I said this wrong. All right. When the power, I had it written right the first time. I'm sorry. When the power is less than or equal to 1, right? So let's back up there, right? When the power is less than or equal to 1, that means the series diverges, right? So since 1 is less than or equal to 1, right? Okay, then we know that this series diverges, right? If the power is bigger than 1, then the series converges. Okay, now, so how can we compare? These two series? Well, let's write down the terms of the two series, right? And let's see how they compare to. Let's see how they compare to one another, right? Okay. So, what's the relationship between 1 over 2 plus square root of n and 1 over n? Is one of these quantities bigger than or equal to the other, or is one of these less than or equal to the other? Okay. Well, I think probably the correct order is 1 over 2 plus the square root of n. I think that's going to be bigger than or equal to 1 over n. Now, why do I think that? Well, I think that because, no, square root of n is less than n, correct, right? That's always the case, right? So square root of n is less than or equal to n, right? When you take the square root of a number, that's going to give you a smaller value, right? If the number is bigger than or equal to 1, when you take the square root of a number, you'll get smaller than the original number. But of course, right, our index here is bigger than or equal to 1, right? So since this is true for n greater than or equal to 1, right? Okay, square root of n is less than or equal to n. So look, so that means since square root of n is less than or equal to n, that means this denominator, right, is going to probably be less than this denominator, correct? Square root of n is less than n. So this denominator is going to be less than or equal to this denominator. And when you make the denominator of a fraction smaller, that means the fraction gets larger, correct? So I'm thinking this fraction is going to be bigger than this one because this one is going to have a smaller denominator. Let's check that a little bit more carefully. So what I'm going to do is let's cross multiply here in this inequality, right? So I can simplify this inequality by cross multiplying. So I'm going to take the n times the 1, and then I'm going to take the 2 plus the square root of n times the 1. So I come up with this inequality, n greater than or equal to 2 plus the square root of n. So I'm wondering, when is that going to be true, right? Okay, just test a few values for n. So when n is equal to 1, what do you get? Well, you get 1 greater than or equal to 2 plus the square root of 1. Well, that's not true, right? What about if n is equal to, let's try another perfect square here. What about if n is equal to 4? So we get 4 greater than or equal to 2 plus the square root of 4, right? Oh, that is true. What about if n is equal to 9, another perfect square? Then we get 9 greater than or equal to 2 plus the square root of 9. Oh, that also is true, right? So notice as n gets larger, which of course is what's happening in this series, correct? Your index is getting larger. If n gets larger, eventually, right, this inequality is true, which means that 1 over 2 plus the square root of n is going to be bigger than or equal to 1 over n. So that means that past a certain index, right? Actually, it looks like past the index 4, right? The terms of this series are going to be bigger than or equal to the terms of this series, right? These numbers that you're adding up in this series are going to be larger than the numbers that you're adding up in this series. But this series already diverges, right? You know this series diverges. It already adds up to an infinite quantity. So these larger numbers are also going to have to add up to an infinite quantity, right? Because these numbers are larger than these. So there we have it, right? We know that this series diverges because its comparison series diverges, and the numbers in this series that we're adding up are bigger than the numbers in this series. Well, at least they're going to be bigger once your index is past the number 4, right? But that's good enough, right? Once your index gets beyond 4, doesn't count for n equal 1, 2, 3, right? But once your n value gets 4 or larger, then the terms of this series are bigger than the terms of this series. And so since this series diverges, this series must diverge as well. I guess we could have compared this. I didn't choose a good choice for my comparison series, right? It might have been easier to compare this to, instead of to 1 over n, it might have been easier to compare this to 1 over square root of n, right? And because, see, 1 over square root of n certainly looks like 1 over 2 plus square root of n, right? But, and we know already this series diverges. Oh, no, well, I take that back, okay? This series also diverges because this is a p series, right, where the power is 1/2, which is less than or equal to 1. No, I take that back. This wouldn't have been a good, I'm sorry, I take that back. This would not have been a good comparison series, okay? It looks like it, but it wouldn't have been a good comparison series because of the relationship between the size of the terms. So never mind what I just said. Okay, I think my first choice for comparison was correct. Okay. All right. Well, so there is the there's examples there of the so-called direct comparison test. But what's the direct comparison test is, as you can see, it's a little bit messy, right? Because what you have to do is, you have to compare the terms of the series, right? And that, you have to have one series where the terms are always bigger than or equal to, or less than or equal to the terms of the second series, correct? And that's, you can kind of see it in this example, right? Is that sometimes that determination is hard to make. So let me show you a simplified version of this test, which is sometimes a little bit easier to use. Okay. All right. So this is called the limit comparison test. So again, you're going to be given some series, right? And you want it. So this is a new series that you don't know anything about. And you want to decide if this new series converges or diverges. But you have another series that you already know something about, right? So imagine this is the new series and this is the old series, okay? So you're still doing a comparison with from a new series to a series that you already know something about. But how we do the comparison is we're going to take the terms of one series and divide them by the terms of the second series, and then we're going to take the limit of that quotient as your index. N goes to infinity. All right, so that's where the term limit comes in. And it turns out that when you compute this limit, if this limit turns out to be a finite, so not infinity, but positive, not 0, cannot be 0. Okay, all right. So if it turns out to be something between 0 and infinity, then guess what? That means that either both of the series converge or both of the series diverge. All right, so let me repeat that. So again, this is another comparison test between two series. So you have a new series that you don't know much about, but you have a pre-existing series that you do know about its convergence or divergence. All right. So you have to sort of invent this series that you already know something about, right, when you're given the new series. But what you do is you form the quotient of terms in the of the two series, and then you take the limit of that quotient as n goes to infinity. And if that limit turns out to be between 0 and infinity, it cannot be 0 and it cannot be infinity, but if it turns out to be something between 0 and infinity, then you know that either both of the series converge or both of the series have to diverge. Okay? All right, so you'll see in a moment here when we look at some examples of this, right, how to use this test. But that's the basic idea of the limit comparison test. But again, it still is sometimes difficult to use because, again, you're given a new series and you're trying to decide if the series converges or diverges, and you still are comparing that to a pre-existing series that you know converges or diverges. So you have to make this choice of what series you're going to compare the pre-existing series to. So you still have to pick that out. But once you've picked that out, then it's not quite as complicated as the comparison test, the direct comparison test, because now all you have to do is compute this limit, right? Now you're saying, well, that limit might be difficult to compute. Yeah, it might be difficult to compute, but you're much better at computing limits now than we were earlier in the course, because remember, you've got L'Hopital's rule available to you, right? So don't forget, L'Hopital's rule is great for computing the limits of quotients, right? So I think we'll get a chance here to use our skills with L'Hopital's rule. All right, we're going to take a look at some examples of using the limit comparison test. But let's pause there for a moment, okay, and then we're going to come back and look at our examples. Okay, so let's take a look at an example of using the this so-called limit comparison test. So what we're trying to determine is, does this series 1 over 2n plus 5, right, does that series converge or diverge? And so first, just like with the direct comparison test, we have to decide if there's a series that we know something about that we can compare this series to. And so sort of the trick here, or it's not really a trick, but something that's really helpful in helping you pick out a series that you might compare this series to is sort of ignore the constants in the formula for each term, right? Because as n gets large, the index, right, it's the index that's changing here. And as n gets large, these two constants, the 5 and the 2, sort of become irrelevant because they're going to be much smaller than the size of n, right? So if you sort of ignore those constants, right, so I'm just going to sort of temporarily scratch them out here. Notice what you get is just 1 over n, right? You get this series. And this is the harmonic series, which we've mentioned several times. This is a p series, and this diverges, right? So that's what we're going to try to compare this series to, right? Because again, this series sort of resembles this one in some sense, especially when n gets really large, right? The terms of this series are going to look similar to the terms of this series, correct? So that's why this is a good choice, maybe, for comparison. All right, now, but unlike in the direct comparison test, I'm not going to try to compare 1 over n to 1 over 2n plus 5 and try to determine which one is larger than the other, okay? Instead, I'm going to take the quotient of these terms, 1 over n and 1 over 2n plus 5, and then I'm going to see if I can figure out what the limit of this is as n goes to infinity. Now, that's a chore in itself, right? But again, as I mentioned, right, we're pretty good at evaluating limits now, so maybe we have a chance of evaluating this, the limit of this big quotient as n goes to infinity. So let's try to do that. So first, we let's simplify this complex fraction, right? So if you take 1 over n and divide it by 1 over 2n plus 5, that's the same as taking 1 over n and multiplying it by, right, 2n plus 5 over 1, right? So take the reciprocal of the denominator and multiply, right? And so you end up here with the limit as n goes to infinity of 2n plus 5 over n. And that is easy to evaluate that limit using L'Hopital's rule, right? Because as n goes to infinity, the numerator is going to infinity, right? And the denominator is also going to infinity, right? As n goes to infinity, obviously n is going, the denominator n here is going to infinity, right? So you get this indeterminate form, infinity over infinity, right, if you try to substitute infinity n directly for n. But that's an indeterminate form that L'Hopital's rule applies to, right? So infinity divided by infinity. So we know that the limit as n goes to infinity of this quotient will be the same as the limit as n goes to infinity of the derivative of the quotient of the derivatives, right? Take the derivative of the numerator, which is 2, and the derivative of the denominator, which is 1. So, so this limit is the same as this limit, but this limit is the limit of a constant, right? 2 over 1 does not depend on the value of n, so this limit is just 2. All right, nice. So we can evaluate this limit, and notice that it is between 0 and infinity, correct, right? 2 is definitely between 0 and infinity. That means then that the direct comparison test, the limit comparison test worked, right? Because the limit of this quotient was between 0 and infinity. So either both of these series converge or both of them diverge. But since we already know that 1 over n diverges, right, then that means that 1 over 2n plus 5, this series also diverges. See how easy that was? So we didn't have to examine some sort of inequality, right, and figure out, when terms are bigger than, when the terms of one series are bigger than the terms of the other series, right? We just take this limit, and it was easy to evaluate with L'Hopital's rule, and so we can immediately decide that both of these series converge, right? That's the kind of the power there of the limit comparison test. But still the difficult thing about the limit comparison test is when you're given a new series, trying to choose the series that you're going to compare it to. That's always the tricky part. All right. So mostly in these examples, I've given you hints. Or told you actually what I think you should compare the series to, but I'll try to give you ideas of how I arrived at the comparison series. Okay. All right. So look, here we're trying. So this is a complicated series, right? We're trying to determine if this sum 1 over 3n squared minus 4n plus 5, right? As n goes to infinity, right? We're trying to decide if the sum of fractions like this add up to infinity, right? In other words, does this series converge or does this series diverge, right? So why did I choose 1 over n squared as my comparison series? Well, one reason is I know what happens to 1 over n squared. It converges because this is a p-series, right? Again, you've got an index raised to a power. The power here is 2, which is bigger than 1, and in a p-series, if the power is bigger than 1, right, the p-series converges. If it's less than or equal to 1, the p-series diverges, right? But if it's greater than 1, the p-series converges. So I know that this series, I already know that this series converges. So I'm hoping, what I'm hoping to do, right, is use my knowledge of this series, right, to check on this series. Now, why did I choose 1 over n squared? Well, again, I'm sort of looking at the terms of this series, right, and trying to simplify them some. So what I'm thinking is, look, as n gets really large, right, as n is going to infinity, first, these constants are kind of becoming meaningless, right? As n gets really large, 3 and 5 are very small numbers, right? So you can sort of ignore, for that reason, the 3 and the 5. Okay, I mean, you can't really ignore them, but for the purposes of comparison, we can ignore them. Now, also, 4n is not going to be anywhere as large as you can also ignore the 4, I'm sorry, as well, right? In addition to the 3 and the 5, because that also is a constant. So I'm just going to sort of lightly scratch that out right now. That leaves me with n squared and n. But again, as n gets really large, n squared is going to be huge compared to n, right? When you square a number, when the number is bigger than 1, right? When you square a number, it makes the number larger. But if the number is really large, like close to infinity, n squared is going to be way bigger than n. So again, I can sort of ignore the n here, right? Because this denominator is dominated by n squared. That's going to be by far the largest value in this denominator when n gets really large. So notice you're left here with just 1 over n squared. That's why I chose this as the comparison series. Now, this converges, right? So I'm going to take this limit as n goes to infinity of the ratio of these two, the ratio of the terms, right, of these two series, and hopefully that limit will exist. And so I can compare these two series, right? So let's see, let's do exactly what we did in the prior problem, right? So this complex fraction, I think once you simplify this complex fraction, so you're going to convert it from a division problem to a multiplication problem, you get, well, let's write it out here. So you get 1 over 3n squared minus 4n plus 5 times n squared over 1, right? So that's the limit as n goes to infinity of n squared over 3n squared minus 4n plus 5. And so now what is this limit going to be, right? Okay, well, again, L'Hopital's rule is going to apply nicely here because as n is going to infinity, the numerator here, n squared, is also going to infinity, right? And the denominator is also going to be going to infinity, right? As n gets really large, again, this denominator is essentially going to be the same as n squared, which will be infinity when n goes to infinity, right? So you get this indeterminate form, infinity over infinity, but that's perfect for L'Hopital's rule. So you can apply L'Hopital's rule here, and actually I think you have to apply L'Hopital's rule twice in this problem, because if you take the derivative of the numerator, right, and the denominator, you get first this quotient, and then you have to take the derivative again to properly finish evaluating this limit. So that gives you 2 over 6, right, which is a constant that is 1/3, right? As n goes to infinity, you know, 2 over 6 is a constant, so it's not changing. So this limit will be 2 over 6, which is 1/3. Oh, cool, right? That is between 0 and infinity, right? Correct, right? And so that tells me then that these series behave the same way. Since this series converges, then this series also converges. So that's actually pretty good. If you can look at this series and determine that it converges, you're doing really well, I think, okay, because that's not an easy series to analyze there. Let's try another one. This one's even harder. All right, so what's happening now with this series, right? So we have the sum from n equal 1 to infinity of square root of n over n squared plus 1, right? Okay, so I'm going to compare this to square root of n over n squared, and I think it's obvious why I chose this as the comparison series, right? Because again, as I mentioned in the prior two examples, as n gets really large, as your index gets really large, the plus 1 here in this denominator kind of becomes meaningless, right? Because n squared is going to be a really huge number, And so you can sort of ignore the plus 1, right, for the purposes of determining if the series converges or diverges, right? You can sort of ignore the plus 1. And when you do that, you get something that looks like this, right? You have square root of n over n squared. And I want to point out now that that series we can analyze easily, because square root of n, we can rewrite that in the usual calculus fashion, right, as n to the 1/2 power. So we have the sum from n equal 1 to infinity of 1 over n to the 3/2 power, right? And this again is a p-series, right? You're taking the index and raising it to a power. And the p-value here, the power is 3/2, which is bigger than 1. And so we know this series is going to converge by our knowledge of p-series, right? Okay, this series is convergent. So I'm hoping I can compare these two series, and since I know this series converges, I'm hoping I will be able to figure out that this series converges as well. All right, so what do I have to do here? I have to take the limit as n goes to infinity, right, of, just take the terms of one of the series, right, and divide it by the terms of the other series, and see if you can compute that limit. Let's see, can we compute this limit here? So we have the limit as n goes to infinity of square root of n over n squared plus 1 times, take the reciprocal and multiply, right? So this is going to be n squared over square root of n. But the square roots of n very nicely there divide out, and we get the limit as n goes to infinity of just n squared over n squared plus 1. And again, you can apply L'Hopital's rule here to evaluate this limit. I think you'll have to apply L'Hopital's rule twice to evaluate this limit, and it comes out to be 1. So that's it. 1 is between 0 and infinity, right? So that means the limit comparison test applies, right? Because we ended up with the limit not 0. You cannot have the limit being 0. If the limit is 0, then this test doesn't work. It's inconclusive. Or if the limit turns out to be infinity, the test doesn't work. So the test is inconclusive. But since this limit is between 0 and infinity, that means the test is conclusive, right? And so since our comparison series converges, then this new series also converges as well. What does it converge to? I have no idea. I don't even know what this series converges to, right? I just know it converges. But and so I don't know what this comparison series converges to. I certainly don't know what this series converges to. But it's some number. All right. Woo. All right. Let's take our last example. Right. Okay. So this one looks really terrible. And all right. So the tricky part of this example is, I think, finding the comparison series. I shouldn't say I think. That's really always the difficulty with the limit comparison test, is finding a series that you can compare to, right? So here my series is n times e to the n. Looks really weird, right? Times 4 over n cubed plus 1. What in the world is happening to this series, right? So these have very complicated terms, right? So you can write out a few of the terms if you want to. Let's see, what would they be here? So if n is 1, you get you get 1 times e to the first power over 4 times 1 cubed plus 1, so that's going to be 5, right? So the first term of the series is e over 5. And the second term of the series is, we would get 2 times e squared over, what in the world do I get when I plug 2 into the bottom here? I get 8 times 4 is, 2 cubed is 8, times 4 is 32, plus 1 is 33. So I get 2e squared over 33. That really strange number, right? And so on and so forth. Okay, so I'm trying to figure out, wow, do these, when I add up all these different terms, right, do they do they add up to a finite number, or do they add up to infinity? All right. So that's, who knows, right? Okay. Just by looking at the terms of the series, impossible to tell, correct? So I need a series that I can analyze to compare this one to. Okay. All right. So here's what I'm gonna here's how I'm gonna try to simplify the terms of this series. First, as I mentioned in the prior examples, right? As n gets really large, n cubed is going to be huge, right? So the 4 is kind of meaningless and the 1 is kind of meaningless. So let's kind of ignore those. So the constant terms, I can sort of, the constant terms and factors, right, I can sort of just ignore those. Now, I can't ignore the n because that's not constant, or e to the n, that's not constant, right? And n cubed is not constant either, so I have to keep those. But when you ignore the 4 and the 1, notice then the n over n cubed you can divide out, right? If you take out the 4 and take out the 1, then n over m cubed is going to reduce, right? And that reduces to just n squared in the denominator. So that's how I come up with this comparison series, e to the n over n squared, which is already kind of complicated, right? What are the terms of this series? Well, it would be, if n is 1, you would have e to the 1 over 1, right? 1 squared is 1, plus, when n is 2, you have e squared over 2 squared is 4, and then when n is 3, you have e cubed over 3 squared is 9, and so on and so forth, right? So, well, that's it. That's what I'm going to try to compare this series to. But I have to figure out, does this series actually, I don't know, does this series actually converge or diverge itself, right? Because I don't know that, right? Because that is not a familiar series to me. That's not a p-series, right? If this were 1 over n squared, that would be a p-series, but this is e to the nth power over n squared. So it's not a p-series, it's not a geometric series. I'm not quite sure right yet. Does this series converge or diverge? But here we're going to use one of our prior tests. So this is one of the first tests we learned. Look, remember, for a series to converge, as n gets large, the terms of the series have to get close to 0, right? Okay, so again, let me repeat that. Remember, if a series is going to converge, if it's going to converge, then as your index gets large, the terms of the series have to go to 0. So what I'm going to look at here is the limit as n goes to infinity, just of the terms of this series. Okay. And I want to know, does that go to 0? Because if that, sorry, this is supposed to be n squared. Does that go to 0? If that doesn't go to 0, then I know that what that means is that the terms of this series are getting bigger and bigger, right, as the index gets larger. And that means then that the series has to diverge, correct, right? So let's look at this limit. And again, we can evaluate this limit using L'Hopital's rule. So take the derivative of top and bottom. So the derivative of the top that's easy, right? That's e to the nth power, because this is an exponential expression. And then the derivative of the bottom is 2 to the n, right? And if you then apply L'Hopital's rule a second time, you end up with the limit as n goes to infinity of, well, the derivative of e to the n is still e to the n, but the derivative of 2n is 2. So you end up with the limit as n goes to infinity of e to the n over 2. And guess what? That's going to be infinity, okay? Because the numerator is going to be getting really large. E to the n is going to be getting really large, right, as n goes to infinity. But 2 is just 2. So you end up with infinity over 2, which is infinity. So guess what? That means this series has to diverge, right? Because the numbers that you're adding up in this series are just getting larger and larger and larger. So if the numbers themselves are getting larger and larger and larger, right, then the sum of those really large numbers is also going to infinity. So this series, so the terms of the series are getting big. That means that the sum of the terms of the series, right, has to be getting big as well. So this series is going to diverge. All right, so that's good. That means I have something I can compare this series to, right? Okay. All right, now let's take the limit as n goes to infinity again of the quotient of these two series, right? So I have n e to the n over, it's going to be an ugly quotient, right, over 4n cubed plus 1 divided by what? E to the n over n squared. All right, so how does that, how can we simplify that complex fraction here with a little bit of algebra? So that's going to be n e to the n over 4n cubed plus 1 times, and then, so take the reciprocal of the denominator and multiply, right? Oh, how nice. So what happens here? The e to the n's divide out. Ooh, just what I wanted, right? And so I have the limit as n goes to infinity of n times n squared is n cubed over 4n cubed plus 1. And that limit we can also evaluate now. That's easy to evaluate using L'Hopital's rule again. Okay, so we can apply L'Hopital's rule and we can take the derivative of the numerator and denominator. And actually, you'll have to take the derivative of the numerator and denominator 3 times, I think. Okay, so you'll have to apply L'Hopital's rule 3 separate times to finally get this to where you can evaluate it. But when you do that, so apply L'Hopital's rule, I think 3 times, not twice, but 3 times, you'll eventually discover that this limit is 1/4. Okay, so this limit does exist. It's between 0 and infinity. And so since this series diverges, guess what? That means this series must diverge also. See, when you take, again, when you take the limit of the quotient of the terms of these two series, and that limit turns out to be between 0 and infinity, that means either both of the series converge or both of the series diverge. But since you know this series diverges, that means this series must diverge as well. All right, so, well, there's 4 examples where the limit comparison test is really helpful, right, to tell if the series converges or diverges. All right, so, oh, but by the way, now, we didn't see an example, but it could happen where this limit of the quotient of the terms, right, turns out to be 0, or if it turns out to be infinity. That happens, and when that happens, that means, that doesn't tell you anything about the series. That just means the test fails, so the test is inconclusive. Okay, so you just have to go on and try something else because the limit comparison test just turns out to not be useful to you in that case. All right, so, well, that we're done. Okay, so that was the last example for the course. Okay, and so remember all the things I told you at the beginning of the lecture, right? The test is coming up, right, on Monday, April 27th. Don't forget to finish your homeworks, right? If you go over on your homework, then, you know, if you run past the due date on your homework, remember you can apply for an extension, automatic extension. The policy is a little bit more generous than it was in the beginning of the semester. You get 80% of the points, 80% of the points that you that you earn after the due date. Okay, so use those automatic extensions if you need to. Okay, on your homework. All right, and so this is the last time I'll be speaking to you directly, but don't forget that you can sign on to your, you can log into my Zoom office hours, and Taylor will be holding her SI session on Monday, April 27th, the day of the test, and she will have or there will be, I don't know if it will be with Taylor or with someone else, there will be a final exam review, but I do not know the date for that, okay? So I'll have to find that out. All right, so you'll be watching for that as well. There will be a final exam review if you are a person who is going to be taking the final exam. Okay, so best wishes on test number 3, and best wishes with the final exam. As always, stay safe, right? So keep using those good practices, right? Social distancing and washing your hands and wearing masks, right, when you're in a crowd. Okay, so that so that you don't get sick. All right, so I will talk to you guys maybe individually later. All right, bye bye.